We continue with our next speaker, Pedro Benedini from University of San Carlos, ICMC, San Carlos, about the geometry of corank 1 surfaces in R4.
Thank you. Do I need to use the microphone? Because I really hate it. No? So that's okay. Good morning. My name is Pedro. I'm a PhD student at ICMC under the supervision of Professor Cidinha and also Raul Sinha from Valencia. And thank you very much for this opportunity. It's one of a kind opportunity. Thank you. I will talk about the geometry of corank 1 surfaces in R4. And to do such a study, we need to look at the rich literature concerning not only surfaces, regular surfaces in R4 and R5, but also singular surfaces in R3. And here, I put some authors that have provided us the background, and I hope I didn't forget anyone that it's in here. And, I'll split my talk in two parts. In the first one, I'll talk about the second order geometry of any corank 1 surface in R4. And as Raul promised on Monday, the second part will be dedicated to the flat geometry of the singularity I1. This is the importance of this singularity is that this is the first one that appears in the classification of Klotz, Popp, and Rieger of 2007. First, to study the second order geometry of such surfaces, we need this construction. We'll consider M tilde a smooth surface, G a smooth map with Q a corank 1 point of G, and M will be taken as the image of M tilde under G, and G of Q will be P. We can take a local coordinate system phi of M tilde, and F, defined by this composition, will be a local parameterization of our surface M at P. The tangent line of the surface M at P will be the image of the differential map G at Q, and the normal hyperplane of M at P will be the subspace satisfying this condition. And it's important to notice that the dimension of NPM is 3. The first fundamental form is defined in a canonical way. It's important to say that we needed that construction before because all the second order geometry will be taken in this space. So that's why we need the previous construction. And the first fundamental form is defined in a very canonical way, and it induces a Riemannian pseudometric, not a metric, on the tangent space of M tilde at Q. The second fundamental form is defined in the basis of Tk M tilde, and we can later extend it in a unique bilinear way to the whole space. And it's also important to say that the definition of the second fundamental form does not depend on the choice of local coordinates on the surface M tilde. So it does not depend on the choice of the phi, the application phi. Also, for every normal vector in NPM, we can define the second fundamental form along this direction, as we see here. And if we take an orthonormal frame of NPM, we can write the second fundamental form as a summation of the second fundamental form along each direction of the frame. And furthermore, if taking this orthonormal frame, we can represent the second fundamental form as this matrix. That means the matrix of the coefficients. Now I'm able to define the curvature parabola. This definition was first made by Martins and Ballesteros in 2015. And the curvature parabola, delta p, is the image of the map eta q defined by the restriction of the second fundamental form to the subset of unitangent vectors CQ. So the curvature parabola is a plane curve that can be parametrized in this way by eta using an orthonormal frame, and I must say that the curvature parabola may degenerate into a half line, a line, or even a point. In 2016, Mendes and Nuño-Ballesteros, they showed that there are 4 A2 orbits in a space of 2 jets of corank 1 maps from R2 to R4, as we see. And the interesting thing is that the curvature parabola is a complete invariant for their classification, in the sense that the curvature parabola can distinguish the 4 orbits, as we see. So here we have a parabola. In this case, we have this normal form if delta p is a non-degenerate parabola, this normal form if we have a half line, a line, or a point. Oh, this is big. We show that just using a smooth change of coordinates in the source and isometries in the target, we can write any corank 1 map from R2 to R4 in one of the following ways, depending only on its A2 normal form. It's a little big. I'll let you get all over it. Okay. Well, this theorem is very interesting, and it attests that the curvature parabola contains all the second-order information of a surface, in the sense that 2 surfaces have their 2 jets equivalent under the action of R2 times O4 if and only if there is a linear isometry that maps one curvature parabola to another. And inspired by the study of regular surfaces in R5, here I define the affine curvature plane and the curvature plane itself. The affine curvature plane is the plane that contains the curvature parabola delta p when it does not degenerate, the plane that contains the image of the second fundamental form when delta p is a line or a half line, and the plane parallel to the plane yz through delta p, of course, when the delta p is a point. And we define the curvature plane EP as the plane parallel to the affine plane, but passing through P, that it's the orange of our system.
Excuse me, could you repeat the definition of curvature parabola?
Oh, the curvature parabola? Yes, of course. The curvature parabola is the image of the second fundamental form when we restrict it to only to the unit tangent vectors. So we have the second fundamental form applied to x when x is a unit tangent vector of the TKM, the tangents.
The space of quadratic map.
Yes.
Okay.
You're welcome. Well, so we have the affine curvature plane and the curvature plane itself. Here we have an illustration of the previous definition. We have the curvature parabola, the affine curvature plane, and the curvature plane itself. Well, now I can define the concepts of asymptotic and essential binormal directions. A vector, a non-zero tangent vector x is an asymptotic direction if there is a non-zero vector in EP on the curvature plane satisfying this condition. In such case, we say that this vector is an essential binormal direction. But we may have also non-zero vectors in NPM, vectors that do not belong in P, but also satisfy the previous condition. And we call these vectors binormal directions, just binormal directions. In order to proceed with the following results, we shall decompose the normal hyperplane in a very helpful way. We shall write it as the direct summand of EP and EP orthogonal. And we'll consider an orthonormal frame satisfying this condition. And as we already know, we will be able to write the matrix of the coefficients of the second fundamental form using this frame. This lemma gives us a criteria to identify asymptotic directions, in the sense that a non-zero vector x will be an asymptotic direction if and only if this condition holds. It's important to notice that we only use the curvature plane. Its orthogonal complement, it didn't make any difference. Well, we know that when we have the parametrization of delta p, the curvature parabola, the eta parametrization, as I defined earlier, we know that every parameter y corresponds to a unit tangent direction x in CQ, the subset of unit. I must say that this concept of measured is based on our definition of the pseudometric induced by the first fundamental form. And we'll define the null tangent direction x equals to 0, 1. It's defined as the corresponding to the parameter y infinity in the following way. If the curvature parabola is a line or a half line, eta of y infinity is equal to eta prime of y infinity, and they are equal to this vector. It's important to see that they are equal. It will be important later. If delta p is a point v, of course, eta of y infinity must be v, and its derivative must be 0 since it's a point. And if delta p is a non-degenerate parabola, these vectors, they are not defined. Well, using this lemma, it tells us that a tangent direction given by a parameter y is asymptotic if and only if those two vectors, they are collinear, where pi is the canonical orthogonal projection into the curvature plane. And by abuse, we say that this parameter y corresponding to an asymptotic direction is also called an asymptotic direction. And now, having the this lemma in mind, we are able to count the number of asymptotic directions for each possibility of delta p. When delta p is a non-degenerate parabola, we may have 2, 1, or 0 asymptotic directions, depending on the position of p. When p lies outside the curvature parabola, we have 2 asymptotic directions. When p is on the parabola, we have just 1. And when p lies inside the curvature parabola, we have non-asymptotic directions. When delta p is a half line, we have 2 asymptotic directions if delta p is not radial, and if it is, all directions will be asymptotic. When delta p is a line, we have 1 asymptotic direction if delta p is not radial, and if it is, again, all directions will be asymptotic. And at last, when delta p is a point, once again, this is the more degenerate case, all directions will be asymptotic. Well, as I also promised, I'll talk a little bit about the umbilic curvature. And in order to do so, I need to consider a very special orthonormal frame of NPM. we will consider a frame that if delta p is a non-degenerate parabola, the second fundamental form will be written in this way, but we already know that it's possible. But when delta p is a degenerate parabola, the second fundamental form will not depend on Ni3. Besides, if x here, it's important to see that I'm taking any tangent direction, it's not a unit tangent direction. Besides, when x is a unit tangent direction, the last component of each equation tells us only about the position of the curvature parabola in the space, in the sense that the second fundamental form restricted to the unit tangent vectors will not depend on the third component up to sinus. So, with this in mind, we can define the umbilic curvature, as we see. And geometrically, the umbilic curvature measures the distance between the affine curvature plane and the curvature plane itself, when delta p is a non-degenerate parabola, the distance between the line that contains delta p and p, when delta p is a line or a half line, and the distance between delta p and p itself when delta p is a point. This definition was a generalization of the definition given by Martins and NuñoBallesteros in their paper, but also we use the definition of umbilic curvature for regular surfaces in R5 given by Carmi. Well, a powerful tool to study the geometry of a surface is to study its contact with some other model objects. In our case, we'll study the contact between our surface M at P with hyperplanes. And such contact is measured by the singularities of the high function. Here we have the high function hv, where v belongs to the unit sphere, and f is a local parameterization of M at P. And the study of the high function gives us this theorem. We will know that the high function will be singular at the point P if and only if the vector v belongs to the normal hyperplane. Furthermore, if delta p is not a point, the high function will have a degenerate singularity at P if and only if the vector v is a binormal direction. And when delta p is a non-degenerate parabola, the high function has a singularity of type sigma 2, if and only if the vector v is orthogonal to EP or the umbilic curvature is 0. Also, when delta p is a line or a half line, the singularity is of type sigma 2, if and only if this condition holds. And at last, when delta p is a point, the singularity of hv is degenerate for all normal vectors and is of type sigma 2, if and only if this condition holds. So we obtain conditions on V and also using the umbilic curvature. A hyperplane through P and orthogonal to an essential binormal direction is called an oscillating hyperplane. And having in mind the previous result and this definition, we have this consequence. If delta p is not a point, a hyperplane has a degenerate contact with M at P if and only if this hyperplane is orthogonal to a binormal direction V. Moreover, if V is an essential binormal, the hyperplane will be the oscillating one. And well, yeah, that's all. Now I'll start the second part of my talk. And in this part, I'll study the flat geometry of this singularity, A1, given by this A model. And now I'll do it in two different ways, as Raul also promised and also did. Well, the first approach is to study, to give a Rx classification of germs of submersions from R4 to R, where X is our model surface given by F. And then, using these normal forms, we will study for each orbit the high function related, and then we will study the flat geometry of this surface. First, let me remind you that Rx is a subgroup, a geometric subgroup in the sense of daemon, of diffeomorphisms that preserve our variety, our model variety X. Well, in order to obtain such classification, we need the E4 module of vector fields tangent to X, denoted by theta X, and also called their log. And we will obtain these vector fields, we will integrate them, and then to obtain the diffeomorphisms in Rx, and using the complete transversal method for the subgroup Rx, we will obtain the classification. In our case, I is the ideal of polynomials defining X, and it's important to see that we have 4 of them, 4 equations. So it's a little hard to calculate this module of vector fields. And a vector field will belong to the der log if and only if this condition holds. I said it's difficult because in our case it's not a complete intersection, so it's harder to calculate it. But we were able to do it using the software Singular. In using it, we got the module, the der log. And it's important to see that only the first seven ones have non-zero linear part. So we obtained 13 vector fields in this module. And here, now we have the Rx classification of submersions from R4 to R, which have codimension less or equal to 3. Well, now in here, of course, we have the orbits. For our model surface X, we know that the tangent space is given by this vector. The tangent cone is the plane XZ, and the curvature plane is the plane YZ. So as I said, for each orbit G that we got from the last theorem, we will study the fiber, G equals to 0, and the high function given by this composition, where F is our singularity from the list, the I1 singularity. So let's do it. The first fiber is transverse to both the tangent line and the tangent cone, and it contains the curvature plane. And in this case, the high function is regular. The second fiber is transverse to the tangent cone and to the curvature plane, and the high function has singularity of type AK-1. The third fiber contains the tangent cone and it's transverse to the curvature plane, and in this case, the high function has singularity of type A1, aka Morse. And the last fiber contains both the tangent cone and the curvature plane, and in this case, the high function has singularity of type A2. So these are the generic singularities that we have for the high function. So with this, I finished the first approach in the study of the flat geometry. The second one, as Hao also promised, he made a lot of promises. We were able to obtain a normal generic form for any surface whose parameterization is A equivalent to this one. And we made this just using smooth change of coordinates in the source and isometries in the target. And now, once again, we will look to the high function, but now using the previous generic normal form we got. Once again, V will be a vector in the unit sphere. And now, pi V will be the orthogonal hyperplane to the vector V. And we already knew, but once again, the high function will be singular if and only if this V1 is equals to 0, which is equivalent to the hyperplane pi V containing the tangent direction of the surface. Now, we will study different possibilities for the vector V in order to get different positions for pi V, the tangent cone, and the curvature plane. And these possibilities will give us conditions over the coefficients of the generic normal form for each possible singularity of the high function. In the sense, for example, if V is this vector, the hyperplane pi V is transversal to the tangent cone and to the curvature plane. And the high function will have singularity of type A1 if and only if V isn't an essential binormal direction. It means that the hyperplane pi V is not the oscillating hyperplane. The conditions for A2 is now V will be an essential binormal direction, which means that pi V will be the oscillating hyperplane. And we have also this condition. And for singularity of type A3, we have those conditions using the coefficients of the generic normal form we got. When pi V contains a tangent cone and is transverse to the curvature plane, the vector V is given by this one, and the high function will have singularity of type A1 or Morse. And at last, when delta P contains both the tangent cone and the curvature plane, V will be given by this vector, and the high function will never have singularity of type A1, A2 if and only if the umbilic curvature is non-zero, and A3 if and only if the umbilic curvature is 0. This case didn't appear in our first approach because it's not generic. Well, this is it. Thank you. I hope I didn't bore you to death. And once again, happy birthday, Federico.
Are there questions or comments?
Parabola curvature in the singular surface.
Yes.
Have some relation with the ellipse curvatory surface, regular surface in R4?
Yes, as a matter of fact, there is a relation. Hao and I, we proved that there is a relation between the ellipse, ellipse of curvature from regular surfaces in R4 and the curvature parabola of surfaces in R3. So, spoiler alert, there will be a paper soon just giving this information. Okay, so it's answered. Just wait and see the paper.
Any more comments? Okay, thank you.
Thank you.